Let's continue the discussion of linear classification models. With this small data set of shapes with width and height attributes, the notion of standing here in this data set is that whenever the height is greater than width is standing, or yes, according to the standing class, and if width is greater than height, then it's in the negative class. It's not standing but lying. So in the data set here, whenever you see the width greater than height, then it's in the negative class. Whenever height is greater than width, it's in the yes class. So there is a linear relation between the height and the width, two variables here for the classification of standing versus lying. Now we had this idea of the linear classification using the centroids of the data points. Again, emphasize the idea of a linear classifier. Let's say the width is V1, the height is V2. And so for this particular data set and the classification problem, ideally, if you can identify this line, this straight line here, such as V1 minus V2 equal to 0. Or I should say V2 minus V1 equal to 0. Okay, so this is a linear function. It's a linear combination of the two variables here, which forms the line here that separates the two classes. And so when it comes to the classification, when you try to consider a data point here, whether it should be predicted positive or negative, you can plug the value into this linear function, and if the result is positive, then you can classify that data point as positive. If the result is negative, then you can classify that as negative. And to identify this linear function, this straight line on a two-dimensional space with two variables here, the between centroid strategy is to first compute the centers of the blue class, the positive class, and the centroid of the red or the negative class. And then the idea is that the separation line should be somewhere in between the two centroids, or in the middle of the two centroids. And so we are going to find the middle point between the two centroids and draw a straight line, or a linear function actually, perpendicular to the line connecting the two centroids. Okay, so on this two-dimensional space, of course, the linear function is a straight line, but it could be a plane, a hyperplane in a higher dimensional space. To find out this linear function is actually quite simple based on some vector computation. So this is not the problem here. The problem, however, is that this idea of centroid-based classification for linear classification is very sensitive to variance or noise in the data. Whenever the data points changes a little bit, so for example, if the negative data points move here, suddenly the centroid will be moved toward this side, and the linear equation will be greatly impacted. And so this idea basis the centroids is very much subject to the distribution of the data. And when you have a greater variance and a difference between the training data and the testing data, the model is not going to work quite well. So let's consider this example, a real life example. So think about the border between the United States and Canada. So we have two countries here, two independent nations. And how do we separate these two nations? We have the border lines, right? So we have the border line that separate the two countries. It doesn't matter where the centers of the two countries are. Even if the two countries of the same size, the border is rarely halfway between the centers, right? So rather, it is much more relevant and more important to find out where cities and landmarks and populations are on the border to separate the two countries. We can look at cities such as Detroit, Vancouver, and Toronto, among others, that actually help define the US-Canada border. So for classification, we can borrow this the same idea here. It matters not where the centroids are, but where the borderline data are. And so the support vector machines, or SVM, is a method focused on the border populations and draws the border based on the so-called support vectors, data points that are located on the boundary and together form the border. We can start by connecting a number of data points within the same class to construct a line, and then consider some of these lines or pair of data points as potential support vectors. And so when we connect these data pairs in the same class, we are finding potential candidate support vectors to form the borders. And in order for them to qualify as support vectors, they have to meet certain conditions. For one, if the two data points form a line, then the requirement here is that all data points in the same class fall on one side of the linear function. And then most, if not all, data points of the other class reside on the other side of the line. So let's look at an example here just to make sense. So for example, this is perhaps some more data points in the shapes data set. Okay, so again, the blue is the positive class for standing, the red is the negative class for not standing or lying. And so to find out which data points can be potential support vectors, we want to consider each pair of data points. So we can look at, for example, the data point here and the data point here and draw a line between them. Okay, so this is a line formed by these two data points. And we are going to look at do all the data points in the same class fall on one side. And so in this case, all the blue data points are on one side of the line. So the first condition is met. The second condition is that data points in the other class should be on the other side. Okay, and so when we look at the red data points, they are also on the same side. And so this is not a support vector that we should consider. So we dismiss it. Now let's take a look at another. So let's consider these two data points and we can draw a line also. And in this case, we'll see that neither conditions are met, right? So the blue class, the data points are divided into two. For the red class, they are also divided into two. So this, again, is not a candidate for support vectors. Now, if we look at the two data points here, and they form a line right here, okay? This line here, and we look at the blue class, the data points in the same class, they're on one side of this line. the red data points are on the other side. So this particular line here satisfy both conditions for support vectors. So this can be, these two data points are potential candidates for support vectors. Now, to go a step further, we need to see what kind of margin the support vector creates by forming the line. So what we do here is to, in addition to this line, we are going to also find a data point on the other class that is closest to the line here. And it turned out that the data point that is closest to the straight line here is the data point right here, and we can draw a line perpendicular to the support vector line, the candidate support vector line. And this line, the length of this line is particularly the margin between the two classes. Okay, so how wide this margin is important. And of course, we want the margin to be as wide as possible to separate the two classes as far as possible. Okay, so this is one candidate support vector. Okay, so 1, 2, 3, these three data points form a support vector of margin. Okay, but this is not the end of story. We need to look at other candidates to see which ones create a bigger margin. So if we look at another candidate here, so these two data points, they form a line, so we can draw a straight line between them. Okay, and this line also satisfies the two conditions that we mentioned earlier. So the red falls on one side, the blue data points are on the other side of this line, and then we find the closest data point on the other class in the blue, and draw a line perpendicular to this support vector line, and this is the margin. And so it looks like visually we can tell that this is creating a bigger margin. So in the end, between the earlier one that we found and this one is definitely a better candidate. So in the end, this may be the final support vectors that we find. And so we have three data points that define the border or the margin between the two classes, 1, 2, and 3. So this is the basic idea of finding the linear function using the support vectors. And so the key here is really to find the data points that form the border. And so in the end, when you find this margin, that is in between these two border lines. Okay, so so that is a way of SVM, which works quite well with many different types of data sets, because it's not subject to the variance of all data points, but rather it's more focused on just a few data points closer to the other class. Now let's look at another idea of linear classification using perceptron or a single layer neural network. So a linear function can be visualized actually as a one layer neural network. So let's suppose this is V1 is for width, V2 for height, and then we'll also have a variable for bias, which is just something beyond the variables here. But so we have three inputs, and for each input, we are going to have a weight associated with the input. Okay, so for this bias variable, the value is always 1. Okay, but there is also weight of W0 associated with it. And then for V1, we have a W1 weight. For V2, we have W2 weight. And this sum is a weighted sum of the values. So this sum is essentially Wi Vi, okay, which is the linear combination of W0 times 1 plus W1 times V1 plus W2 times V2. Okay, so this will be the sum of all the input variables. And then in order to predict which class the data should belong to, then there is going to be a step function to decide which way it should predict. So a step function can be something as simple as this. So let's suppose in the case of the shapes data here, the threshold is really 0. Okay, so we can have a step function, something centered on 0, where if it's greater, so if it's greater than 0, then you are going to predict the outcome to be 1, which is a positive class. Okay, if it's less than 0, okay, so this is less than 0, then you are going to predict everything to be 0, which is the negative class. So this is a very simple, step function with a threshold. Now, how does the single perceptron model learn about the weights? Because to find where the linear equation is to find out what the weights are in this single layer neural network. Okay, so the single perceptron network is to learn by errors, by mistakes. Okay, so whenever we see a data point from the training data, we are going to feed all the data into the network. So for example, here we have a V1 5 for width, V2 9 for height, and then the bias variable is also 1. So we feed into the model. Okay, and now people may ask, what are the W0, W1, W2s? At the beginning, we don't know, so we are going to initialize it with some values. You can initialize it with all 0 values or some random numbers. Okay, and so we are going to start with some values, and then so that we can do some computation, and in the end, we are going to make a prediction. Okay, but on some steps of the process, these values will change, will be updated. Okay, and so how do we update the values is key. Now, let's think about 2 different situations. One, the single perceptron makes a correct prediction. That indicates that the weights must be good enough for this particular data instance to make the right prediction. So in this case, we're not going to update the weights. Okay, so if it's a correct prediction, the weights will move to the next training instance. Now, these weights will be updated only when there is a misclassification. So for example, in the data instance here, the actual class is yes, which is positive. Let's suppose when we feed this data into the perceptron, the outcome is negative. And so we are going to predict 0, okay, or negative. So in this case, it's a false negative case. And we are going to update the weights to correct the problem so that we move away from that situation. So the strategy here is very simple. If the actual class is positive and you make a negative prediction, which is wrong, you are going to add the values to the weight. So here I have 5 for the V1, which is width. So I'm going to add 5 to the existing weight. And then for V2, the height of V2 is 9. Okay, I'm going to add 9 to W2. Okay, so think about this case. This case should be standing. Okay, so so the height, we understand that when it's standing, the height is greater than width. Okay, so when we update the weights, we are adding more value to W2 than W1 because the height of V2 is greater than V1. Okay, so we are updating the W weights differently in this case. Okay, so more weights to height, less weight to width. Okay, so this is 1. And then we also add 1 to the W0 for the bias variable. Okay, so we, in this case, it's a false negative case. We're going to add a positive value 1 to W0. Now let's look at a different case, and then we will come back again to see how overall it's going to adjust the weight in the right direction. And so let's suppose this is a negative case, right? So the standing is no. So this is the negative case. And we know that in a negative case, when the width is greater than height. So we see width is 4. So value 4 for V1, and then 2 for V2. We put the value in, and let's suppose the outcome is greater than 0. So we predict 1, which is standing. Okay, again, this is misclassification. So we are going to think, how can we adjust the weight so that it's moving away from the wrong decision making? So the idea is kind of total opposite from the previous case. So in the previous case, we add weights to the existing weight. Now we take away the weight. So in this case, we are going to subtract the value of V1, which is 4 in this case, from W1. And then we subtract V2 from W2. And so in this case, as you see, in the false positive case, when we make a misclassification, and because the actual class is negative, the width is greater than height. And so when we take away the weights, think about this. We take more away from W1 and take less away from W2. Okay, so these are the only 2 situations when we are going to update the weights. And in the first situation earlier, we add more weights to W2. So we add more. So for W2, we add more. And we subtract less. Right? As you can see here, relatively speaking, compared to W1. Now for W1, in the previous case, we add less. And we subtract more. Okay. And here, this is because of the nature of the relation between the height and weight to predict the standing versus lying. And so in this case, when there are more and more misclassifications with training, we're going to see that W1 will be relatively much less than W2. So potentially W2, relatively speaking, will increase, and W1, relatively speaking, will decrease. And so this may become something positive, this may become something negative. And so in the end, we may see something like minus positive 1 or positive 100, doesn't matter, versus negative 100, positive 100 for W2, negative 100 for W1. And so when in the end, when we plug the values back in, we are going to have a formula something like 100 V2, right, minus 100 because W1 is negative, V1 equal to 0. Now, what about W0? W0 in these two cases, in the first case, with the false negative, we are going to add 1 to W0. In this false positive case, we are subtracting 1 from W0. So W0 is actually going to fluctuate, okay? It will be subtracted and added and subtracted, added. So I think in the end, the value will be relatively closer to 0 than the other values, okay? And so W0 is going to be relatively smaller, much smaller than the other. So we can consider W0 to be 0 in the end. And so in the end, we'll be able to identify this relation. So this relation, of course, this is kind of a rough numbers ideas. And so this is similar to, this should be V1 here, sorry. So V2 minus V1 equal to 0. And so the linear function here is again the relation between width and height. And so if height V2 is greater than V1, then you are going to predict positive. If otherwise, you're going to predict negative. So this is the way how the single perceptron learns to identify the linear function. And again, it's learning by mistakes.